Hello everyone, welcome to my YouTube channel. My name is Dhruvi Lavin. Today we are going to look into the topic digital logic in geoscience and geospatial technology with the help of a case study which is FPGA based earthquake early warning systems. This will be covering this in our subject digital electronics. So let's get started. Okay, so taking an introduction, earthquakes are a global threat. As we already know, they are unpredictable and devastating. Early detection is the key to issuing warnings. Traditional systems are slow, but digital electronics help us to make these systems faster. So we'll be using field programmable gate arrays, or we can say FPGAs, which can process seismic signal in real time with custom logic circuits. That's what this project is all about. Looking into the problem statement, we can see that old school systems take 5 to 10 seconds to detect earthquakes, too slow for the warnings. But also, the noise from cities or winds messes up the signals. We need speed and clarity, and that's where digital logic steps in, reducing latency and filtering noise with hardware precision. Take a look at the graph. So, now we'll understand what is an FPGA. So, FPGA is a chip you can program with digital logic. Inside, it is made up of configurable logic blocks packed with lookup tables for combinational logic, flip-flops or memory, and multiplexers for routing. It is like playground for building fast parallel circuits, perfect for earthquake detections. So basically, FPGA is made up of multiple logic gates like AND gate, OR gate, NOT gate, etc. with combinational circuits like multiplexer, also memory blocks like flip-flops. Objective of the case study is to design an FPGA system to process seismic signals in real time. We are using logic gates to filter noise, detect events, and trigger alerts, all tested in a prototype. It's digital electronics in action solving real world problem. Here you can see the process digital logic is using in the below flowchart. Now taking a look on background on seismic waves. So earthquake may have two waves, which is P waves fast and first and S waves slow and destructive. So in this system we will try to catch P waves early. Digital logic helps here. Gates filter out noise and comparators spot those first signals, giving us head start on warnings. Taking a look on the system overview. So the system consists of sensors to pick up ground motion and analog to digital converter to convert the analog P waves into digital logic, and FPGA processes it with logic circuits like gates, flip-flops, you name it. Then it sends an alert. The FPGA is the star crunching data fast with digital hardware. Have a look at this proper diagram on how the system works. So first of all, we'll get the P waves using the sensors, then it is converted into digital logic using analog to digital converter. Then it is the noise is filtered out using an XOR gate. Then the event is detected and decision making is made. Okay, now moving forward, we'll understand the case study context. Imagine a 50-kilometer square area, which is an earthquake zone like California. We have got 10 sensors installed all over the area, as you can see in the image, then which are capable of tracking magnitude of earthquake 3.0 or greater. The FPGA's logic processes all that data under 2 seconds, which is ridiculous. That's digital electronic making a multi-sensor network work. So now we'll understand the FPGA's design methodology. So how we would build this. So using an X Xilinx FPGA, we coded in VHDL describing gates and registers. The process is writing logic, synthesizing it into a netlist, simulating it, then loading it onto the chip. It's this is the digital design in making from scratch. So this is the processes we used and explained in a simple flowchart. First VHDL and Verilog coding, then synthesis, then simulation, and then implementation. Now we'll look into the digital logic in used in signal processing. So this is the technical part here. So first of all, we are using STA and LTA, which is short-term average and long-term average algorithm to detect seismic events. So short-term average tracks quick changes, long-term average sets a baseline, AND gates compare them, flip-flop holds states, and STA when STA beats LTA, then earthquake is detects. That's how the logic works. So I'll explain it to you again. So basically, STA tracks the rapid signal changes, or we can say P waves, while LTA establishes a baseline. So in the FPGA, AND gates and OR gates, it computes the average, then comparators built from logic sets thresholds, flip-flop stores states. This digital logic identifies P waves amidst noise, triggering alerts when STA exceeds LTA by a set ratio, then earthquake is detected. Now we'll look into the finite state machine design. So to control this, we built an FSM or finite state machine idle analyze trigger. So flip-flops store the states. Combinational logic like AND OR gates handle transitions, all synced by clock. Its sequential logic keeps everything in order. So now we'll look into the hardware implementations. So hardware-wise, we have used a 16-bit ADC, which is analog to digital converter to digitize sensor data at 100 Hertz. Inside the FPGA, it counters time in it, register buffers it, and gates processes it. So GPIO pins trigger alarm, all driven by digital circuits for real-time action. So here in the figure, we can uh, take a closer look in the FPGA mechanism, where here we can see programmable interconnect. Then we can see logic blocks in this light blue square boxes. Then this checker box we can see are the input output blocks, and this orange block is a RAM block, and this silverish type block is the DSP unit. Now the important part, which is the simulation results. So we have simulated noisy seismic data. The FPGA logic nailed 95% of P waves detection under zero point 0.5 seconds. Parallel gates and flip-flops made it fast and accurate. This proves that digital logic is applicable in geoscience and geospatial technology with the help of early earthquake detection. Let us look at the setup with a real world testing setup. So we have made real test using shaker table. We hit 90% accuracy for magnitude of 3.0. Logic based filters like XOR gates cleaned up the noise. It's digital hardware shining in real world. So this prototype was tested with a shaker table, simulating earthquakes, digital filters implemented with logic gates, reduced noise, achieving 90% accuracy, and demonstrate how digital electronics can adapt to practical conditions, refining signal clarity with custom circuits. Looking into the performance metrics, so here we have a bar graph which shows the performance of detection time, false positives, and power. So basically, metrics, if we look into the metrics, so detection is made in 1.8 seconds. There is a 5% false positive tuned by logic thresholds, and just 2.5 watts of power used. So this is an official digital design, making it uh, more speedy and reliable. Now we'll look into the advantages of digital logic in FPGA. So looking at the table, FPGA has a low latency of around 1 to 2 seconds, while CPU has high latency of 5 to 10 seconds. And talking about parallelism, which is like processing data multiply through multiple gates. So FPGA is able to process data through multiple gates, while CPU is working on sequential process. And talking about flexibility, reprogrammable logic, FPGA is based on reprogrammable logic circuits, while CPU is based on fixed software algorithm. So looking at all of this data, we can see that FPGA is 10 times faster than CPU, all thanks to digital electronics. So now we'll look into the challenges we encountered in our design. So Noise drowned simple filters, FPGA resources like LUTs ran tight and high speed logic hit timing snacks. Digital design isn't easy, but it's worth tackling. So, the main challenge we encountered was the noise, like the urban noise can also disrupt this, which can give a false positive. So now we'll look into solutions via digital logic. So solutions are an FIR filter with gates and shift registers to cut noise, optimize code savers to save LUTs, which is lookup tables, and clock logic fixed timings. Digital electronics turns problems into solutions. So now comparing the digital design with traditional systems, so which is basically comparing FPGA with CPUs. So compared to traditional systems, FPGAs slash latency from 5 to 10 seconds to under 2 seconds thanks to the parallel logic. Yes, the FPGAs are costlier, but the performance gain justifies it for critical applications like seismic detection, which is a life saving and can save us from a lot of damage. So to conclude, I would like to say that digital logic in FPGAs make the earthquake detection fast and accurate. This prototype proves that it works. Nextly, we would like to add AI and scale it up. And throughout the video, we have seen that how digital electronics is useful in saving lives, and we have seen the application of digital electronics in geoscience and geospatial technology. So thank you for watching this video. Drop a like if you learned something new. Thank you.